Hey, William, what are you doing?
Oh, Mr. Leong, I'm trying to clean the lens so that we can get a clearer shoot for acid-base equilibrium video.
Okay, but what kind of liquid are you using? Are you sure it's okay for the camera or not?
Well, this liquid is ammonia, and from my understanding, ammonia is mainly used for cleaning solutions, so I think it should be okay, right?
Okay, but isn't ammonia part of this yellow liquid that you release when you go to the toilet? Are you really sure it's okay for the camera?
Yes, I'm sure. Ammonia, because of the chemical properties of ammonia, I'm pretty sure it works. Okay, Mr. Leong, come, let me ask you a question. Do you think ammonia is an acid or a base?
So last time in secondary school, we understood that an acid will dissociate in water to give you H+, but a base will dissociate to give me OH- in water. So if I look at ammonia, NH3, right, it's a little bit weird because I don't see any OH in the ammonia. So I think it doesn't fit into any of those definitions there.
Yes, I think you're right, but that's because you're using the Arrhenius definition, which is something that we learn in the O-levels. Actually, at A-level, there's a broader definition. So maybe let's dive into details, shall we?
Sure, let's go. Let's zoom into the notes. Now, the first definition that we talk about is the Arrhenius definition from O-levels, right? So we say that if you dissolve in water to release me a H+, that's called an Arrhenius acid, and conversely, if you dissolve in water to give you OH-, that's going to be called a Arrhenius base. So the classic example of an Arrhenius acid will be HCl, because you notice that when it dissolves in water, it ionizes to give me a H+. Conversely, the popular base is NaOH, which dissolves in water to give me OH-.
Right, this is the Arrhenius definition. So when we do the Arrhenius definition, we are more interested in H+ or OH-, depending on whether you're acid or bases. Now at A level, what we are more interested in is this definition called the Bronsted theory. Now, what's the Bronsted theory? It says over there, if I'm a Bronsted acid, then generally I'm going to be a proton donor. Now, you notice that a proton is the same as a H+. So these two terms, they are interchangeable, and then a Bronsted base is defined as a proton or H+ acceptor. Now we're going to use one equation to illustrate this. Okay, I need you to go a little bit below. You look at your notes, right, all the way down. Now there's one equation over here, right? So what happens in this equation? Your thought process is, how is the proton transfer happening? Who is receiving it? Who is gaining it? All right, so you can see that H+ generally is transferring from ethanoic acid towards water. So the person who is losing the H+ away will be termed as the acid. So this is the acid, and then the water, who is receiving the H+, will be termed as the base. Now, another thing you want to focus on is the products after they have received the proton or lost the proton. So if you look at ethanoic acid, you'll notice that the product is CH3COO-, and it looks like they occur in a pair. So when things occur in a pair, we term them as conjugates. Alright, so for those who are attached right now, you are a conjugate, just like the both of us, we are conjugates. Aww. Alright, so we call this an acid, will give rise to a conjugate base. And likewise, a base in the form of water, after receiving the H+, this guy will be termed as the conjugate acid.
That's right. So let me summarize this for you. First, you understand that for any kinds of acid-base reaction, you definitely will find two pairs, right? So one of them is green as highlighted. The other one will be the blue one. So let me just emphasize this together with the box. So every time when we take a look at a pair, how do we identify them or how do we define them? It is looking out for the number of that it differs by a proton. Right? So in general, now if you take a look at an acid-base reaction, you'll notice that you're no longer always going to get salt and water. This example over here clearly illustrates that there is no water formed. So at the end of the day, now an acid-base reaction is just simply involving a transfer of proton. So shall we take a look at some examples of an acid?
Right now, onto the next page, you'll see that there's a table over there, and what this table is trying to illustrate is there's actually a relationship between the acid as well as their respective conjugate bases. So if you take a look at the first three, alright, all these are generally classified as strong acids. So you can see they're trying to lose a proton away. The outcome here are conjugate bases, and you'll notice a strong acid will give rise to a very weak conjugate base. And as you go all the way down in the table, you'll realize that ammonia, usually we will say that ammonia is a base, but actually it can be an acid, just that it's a very weak acid. So as a very weak acid, what happens is you will give rise to a very strong conjugate base. So Mr. Leong, you see that there's actually a relationship between them, right? What is the relationship?
So if I zoom into the box over here, you'll notice that if you start off with a strong acid, you will always end up with a weak conjugate base. And of course, the converse is true. If you start off with a weak acid, you're going to end up with a strong conjugate base. So this will work for a weak acid, a weak base and a strong base as well. So William, I'm going to ask you a question.
Okay.
Let's say if I give you a beaker of ethanoic acid.
Okay.
Can you share with me, do you think this solution, would it be acidic or basic?
Well, you say ethanoic acid, right? So I hear the word acid, so I'm going to guess that this thing is going to be acidic in nature.
That's right, William, that's a very smart answer, huh? But actually the answer is that it depends.
Oh, it depends.
Yes, what does it depend on? It depends on the substance that you're going to couple ethanoic acid with. So if I couple it with water, as you see in this example over here, now water is what we call a solvent. So William, do you remember what's a solvent?
Yes, a solvent dissolves the solute.
So in this case, you're telling me that ethanoic acid would act as an acid. So what's going to happen in this equation is that ethanoic acid is going to donate a H plus to H2O. As a result, you get the ethanoic ion as well as H3O plus. Now, if you do it in the presence of HCl, something different is going to happen. This is a surprise because HCl is going to be a strong acid, and in this case, it's going to act as an acid instead. HCl is going to donate a H plus to ethanoic acid, and you're going to result in this very weird looking thing, which is a possibility as well.
So I think the thing we are trying to explain over here is that a particular substance can go either way. It can be an acid, it can be a base. It really depends on what you couple against. And there's one important term to describe this, right? What is that?
We're going to say that ethanoic acid is a amphoteric species. So we're going to use the next page, conceptual test, question 1A as an example to show you how you can approach questions that involve conjugate acid-base pairs. Now, the first part that you should do over here is always to go and recognize the pairs. And I hope it's not too hard for you to recognize that, oh, there is a S minus and S2 minus will be one pair. And of course, the other pair that you see is H2O together with H3O plus. Now, if I take a look at how the proton is transferring, HS minus is going to lose a H plus, and by definition, this must be a Bronsted-Lowry acid. And conversely, H2O is going to gain a H plus, which makes this a Bronsted-Lowry base. So its buddy, the other pair, will be known as the conjugate. So this will be known as the conjugate base. And of course, the purple color one will be known as the conjugate acid. So I think it's time for you to try it out. Pause this video, help me to try out question 1B and question 2 as well. The moment you're done with it, you can continue with this video.
Hi guys, welcome back. Now we have shown you the answers for 1B as well as 2A. Now do a self-check, alright? Now I'm going to talk about question 2B and question 2C, which are a little bit more different, right? Now if you take a look at question 2B, what happens here is you have ammonia reacting with NaH. Now what is NaH, Mr. Leong?
NaH is sodium hydride, which is going to be a strong base that you often see in organic chemistry.
Alright, now the thing that's strange here is that NH3 and NaH, they are both bases at the same time. So it's really a matter of which one is going to be a stronger base, and it turns out that NaH is a stronger base. So ammonia has no choice this time round. It is an acid, so what it does is it donates the H plus away, and after donating the H plus, you'll be forming NH2 minus. Now you realize that H minus here is going to accept a H plus. So they'll be forming H2, and there will be a byproduct, a spectator ion of Na+. Now what happens here is that the Na+ can combine with NH2- and they'll be forming NaNH2. So this is how 2B actually works. Now 2C is also very strange. Now what is so strange about 2C?
You'll notice that both the reactants are strong acids.
Yep, so in the event you have two acids, then again it's a matter of who is a stronger acid and so on, right? So it turns out H2SO4 is a stronger acid. So as a stronger acid, what it does now is it will release the proton over to HNO3, and HNO3 will change into H2NO3+, and you will have HSO4- as the conjugate base of this reaction.
So William, this equation looks vaguely familiar, right? Where have you seen this before?
Yes, I think those who are hardworking, you revise your stuff, you will know that we have actually seen this in Arrhenius. We did a reaction on electrophilic substitution on nitration.
Very good. 2 chops for you.
Yeah.
So the last part over here is we're going to look at the last theory known as the Lewis theory, which is to discuss the electron pair transfer. So instead of dealing with proton H+, now we're going to look at a electron pair. So the definition over here, Lewis acid is going to be somebody who accepts a electron pair. So it's slightly different from a H+. For Lewis base, on the other hand, will be a electron pair donor. So we're going to use the second example to illustrate this idea. So if we look at BF3, I'm going to draw BF3 here together with you. B is from group 13, and you notice that it has an incomplete octet, which means that it's going to have an empty orbital. NH3, on the other hand, is going to contain a lone pair, right? So William, can you tell me, whenever you have an empty orbital and somebody else with a lone pair, what is going to happen?
They're going to do a dative bond
Yes.
from the donor towards the acceptor.
That's right. So that is the case where you see in chemical bonding. Now, if I bring you into acid-base theory, right, you notice that NH3 is donating a electron pair. So it's going to make this a Lewis base, which I have written over here, as well as the fact that BF3 is going to accept a electron pair, which is going to make this a Lewis acid. So for the example, question 3 at the bottom, I invite you to take a read on your own. If you have any questions, right, you can always ask our friendly tutors.
All right, Mr. Leong, just now you were asking me a question, right? Okay, now it's my turn to actually ask you a question.
Okay.
Suppose I have a container over here, all right? And this container, someone measures the pH, and he says that the pH of this solution is 1, right? pH is 1. So do you think this is going to be a strong acid or a weak acid? What do you think?
So if I'm a secondary school student, I definitely say that this will be a strong acid, right?
Well, the answer is not quite, or it depends, all right? Now, if you recall, right, what really determines the strength of an acid, it's not so much the pH, right? It's more of the extent of dissociation that they have, whether the acid is fully dissociated or whether the acid is partially dissociated. Okay, let's run through a simulation for the class.
Sure.
All right, now, if you take a look at this, this picture or this diagram is trying to show what happens when I have a strong acid versus what happens when I have a weak acid. Okay, I'd like to bring your attention to the bottom left, right? So if you look at the bottom left, it's trying to show an equation where HA is reacting with water to form A- and H3O+. All right. Now, if you take a look at the picture, you will notice that the HA is totally disappeared. Why? Because this is a full arrow. Can you notice that? It's a full arrow. So every single thing has dissociated into A- as well as H3O+. So just be mindful of this. A strong acid will fully dissociate.
Now, if I take a look at the weak acid, one of the major differences as you look at the bottom left-hand corner is that I'm going to set up an equilibrium, which means that you're going to see a reversible arrow. I mean, that makes sense with what we understood as a weak acid. It only partially dissociates in water. Now that actually means that at any point of time, you will notice that there's going to be the acid molecule as well as their dissociated ions inside the solution. So this is illustrated inside your diagram. You can see grey molecules as well as the A-, H3O+, all present inside. Shall we go back to the notes now, and let's take a look at the part on strengths of acids and bases. So to summarize, what is a strong acid? It fully dissociates in water, representing by a strong arrow, as a full arrow. Now, some examples you have to be aware are your three most important, most common acids: hydrochloric, sulfuric, and nitric acid. These are what we call mineral acids. Now, on the other hand, the weak acids are typically going to be represented with a reversible arrow, and usually organic acids will be the ones that are weak. So things like ethanoic acid, this one you haven't seen before, is called phenol, as well as hydrogen cyanide. So these are some of the common examples.
Now, so a strong acid, weak acid depends on the degree of dissociation, whether it's a full arrow or partial arrow. I think we kind of expect the same thing for a base as well. Now, if you take a look below, a strong base, as you can see, will fully dissociate, while a weak base will partially dissociate. Now, it's good for you to be aware of some examples, right? Most hydroxides, it turns out they are actually strong bases. So as you can see, this is going to be a full arrow. So the hydroxides will be completely dissociated. That is a strong base. Now, a weak base are organic bases, okay? Organic bases. And these are examples of organic bases like ammonia, amines, generally those that contains nitrogen. We'll learn more on organic chem, right? But as a general guide, if you see kind of nitrogen species behaving as a base, then generally they are weak bases in nature. And you can see this is a reversible arrow that would have given us OH- as the product of this reaction. Now, one major difference you will notice between a weak acid and a weak base is the way that we write the equation. Right, remember, what is the idea of an acid? What does an acid do?
It releases H+.
Alright, so we just want to show that an acid is releasing a H+. Now, there are actually two ways for us to do so. Okay, the first way is really shown on your notes, where you can see acetanoic acid is in the midst of losing H+ away towards water. So water receives the H+, and the end result is you're going to form H3O+. Now, there's a shortcut way for us to actually write this. So I'm going to write this for you here, CH3COOH. Instead of having water, you just go direct into the dissociation. So it will be forming CH3COO- as well as H+. Alright, so the two equations are the same, and it really depends on your school. Some will use the one on top, some will use the one below. Now H3O+ and H+ are actually the same. They're interchangeable depending on how you write your equation. Okay, but with a very big but, when you're dealing with a weak base, now what does a base do?
It's going to receive a H+.
Correct. You must remember this. A base must receive a H+. So if you must release a H+, it is non-negotiable. You must have water present so that you can show H+ is transferring towards ammonia. Alright, so I need you to put an asterisk, put a box on this, just to remind yourself that you must have water inside this equation. So the end result is you'll be forming NH4+ as well as OH-.
So let's summarize this using a more mathematical approach. We're going to look at this idea called the degree of dissociation. It's denoted by this letter called alpha. So the formula is to look at, if I give you 100 molecules, how many of these 100 molecules is going to dissociate? So the fraction over here they're looking out for is the amount of acid that's dissociated divided by the initial amount that you have. So William, let me ask you a question. If let's say you have a strong acid, can you share with me what is the degree of dissociation?
Well, strong acid is fully dissociated, right? So the alpha is probably going to be 1.
That's right. And how about for weak acid?
Well, weak acid has very little dissociation, so the alpha is probably going to be much smaller than 1. And I think there's an approximate value, right? What's the usual value?
Usually it's going to be less than 5%, meaning that it's going to be slightly less, it's going to be less than 0.05. That is the typical kind of weak acids that we see in our syllabus. Okay, now let's move on into question 4. We're going to discuss part A. So if I look at the acids, HCl versus ethanoic acid with different concentration, which one is the stronger acid? So we need to understand that the strength of an acid never ever depends on the concentration. So all these you can just eliminate, you don't really have to care about this. The strength of an acid really depends on the identity. I understood that HCl is always going to be a strong acid, which is going to dissociate fully, and ethanoic acid is an organic acid, so you expect this to be a weak acid, so it dissociates partially. So at the end of the day, even though HCl is at a lower concentration, it is still nevertheless a stronger acid.
I think the main thing is we don't want to confuse the concept of concentration against the concept of strength. Right? Strength is, as Mr. Leong says, is the identity. Right? HCl forever strong. Don't care what is the concentration. Right? Likewise, ethanoic acid forever weak. Doesn't matter what the concentration is. So never look at the values to decide whether something is strong or weak in nature. Okay, so 4A I think was quite a doable question, right? Okay, so we're going to leave something hanging, which we're going to explain in class, right? So I think question 4B is an interesting question. You can see that in both cases, we have HCl and ethanoic acid. Both are acids, and the question is, how much NaOH do I need to react with 1 mole of these 2 particles? Okay, so why don't you try this, and then our teachers are going to explain this to you in class. Okay, so we'll catch up with you very soon in class. Have a great day ahead. Okay, bye.
Nice.